Hello, this is Dr. Hisham Saeed. In this video, we'll go over another example of statically indeterminate axially loaded members. And in this example here, I'm kind of giving a very trivial, easy example. So it's and also relevant example. We have a cable for our iPod. If you remember, probably don't. If you're a little younger than me, you didn't deal with iPods. But they have like the audio cables. So you have one of these cables here, and it's inside. There's copper wire and insulation, and they are bonded together very well. And then the idea, if I connect the cable to the iPod and I hang it, the iPod kind of weights around 30 grams. And the question here is, not yet the question, but I think more data is given to us. So the copper wire diameter and the outer diameter of the insulation, and also material properties of the copper as a material and the rubber of the insulation layer. Now going to the question is, what is the stress in the copper wire when it's loaded with the iPad at one end? And if we look at the cable, these two materials or components of the cross section, the inside is the wire and the outside is the insulation, they together carry the load of the iPod. And the promise here is that the glue or the bond between the insulation and the wire is strong enough so they can actually act together to carry the load. So from statics, you can, if I call the load or the share of the iPod weight inside the wire to be P copper, and the remaining part of it is P insulation, they both will equal to the weight of the iPod. One thing to note here, that weight is different than mass. So I'm giving the mass 30 grams, making it in kilograms by dividing over 1,000 and then multiply by the gravity, 9.81 meter per second squared. So I can come up now with an equation, but I have two unknowns. Like I know that both of the insulation wire resist or carry the load of the iPod of 0.29 newtons, but I want to have that breakdown of how much of it carried by the copper wire and how much is carried by the insulation. So how are we going to solve with that? Two unknowns in one equation. So now kind of compatibility of deformations, or what we call also kinematics, will come to help us. So if we assume again the bond and the glue between the insulation wire is strong enough so they can deform together the same amount, so we can say that the delta copper is equal to delta insulation. Whatever elongation happens in that cable will be the same for the wire and will be the same for the insulation outside of it or around it. So how to calculate delta? It's PL over AE. But for every delta, I will use the corresponding values. So delta copper is equal to P copper times L divided by A copper divided by E copper. And similar corresponding values on the other side. The length of the cable is the same, so kind of like we'll cancel L. I'll lift up with P copper, and all the values are given for the area, and E material property for each material here. So I can now calculate the ratio of P copper to P insulation. So now P copper carries around 10.5 times more the load in the insulation, which is an interesting thing. So kind of the stronger material will be able to carry larger portion of the load. So now I have two equations, and I should be able now to solve for the two unknowns I have. So I plug in the first equation and the second equation. I found that P insulation is that. I'm actually after the load and stress in the copper, not in the insulation. So I will go back and plug it in either one or two, equation one or two. So I figured out now that I have the internal force. Still not done yet. I'm after the stress, and stress is equal to the force over the area, and that's it. I got the insulation, the copper stress that's felt because of the load on the cable here. One thing to pay attention to, the units, if I look at the delta copper equal to delta insulation, kind of a gigapascal of the E copper, 110 gigapascal, I made it up 110, 10 to the power 9. So giga is 10 to the power 9, mega is 10 to the power 6, kilo is 10 to the power 3. So just pay attention to the units here. I can write now the answer as 2.13 10 to the power 6 Pascal, or Newton per meter square, or 2.13 megapascal. So that was a quick example showing how to solve for statically indeterminate axially loaded members by, again, seeing how the information we have about deformation can save us a lot of time trying to guess. Now we can use that information to solve for the extra unknown that we could not solve using only statics. All right, thank you so much. We'll see you in other videos.